Okay, I need to kind of rush through a little bit. Dr. Tyrell wanted to have it talk to me, and that's why I was running late, and he got sidetracked with talking about field trips, so I told him I'd be back up in about an hour, so I'm going to just kind of jump right in here. This is a long chapter, as we recall, a lot of slides, but I already covered about half of them before the break, so I'm going to go relatively quickly through them. Right there. So, okay, this particular chapter deals with program control, iterations to begin with, the for loop and the do while loop, and then we're going to be looking at the switch statement. So we went through the for loop, and I think we started the while loop, the do while, but we'll go through that again. That's there. All right, iteration in greater detail. That's there. So iteration means you're going to repeat things over and over again for a number of times, or an infinite number of times, or a undetermined number of times. The break statement, of course, and these projectors don't like this. It's not the pen because it's a new pen, so that's there. So I can't draw on the slides with PowerPoint. So let me just go ahead and put the pen down and use this here. So iteration is you repeat. The break is you exit immediately. Continue. That's there. You simply skip the rest of the loop. That's there. And this is what I get for starting close to on time. Actually, I was like 5-10 minutes. Okay, and I'm going to repeat these there. A loop is a set of instructions that we repeat over and over again. That's there. Some loops never terminate. That's there. Or they terminate at the end of the day or the end of business cycle or something like that. If you have a loop, for example, at a cash register in a food stall, you would just keep repeating till the next customer, the next customer, the next customer, the next customer. You calculate, the bill for each customer. At the end of the day, you would say end of customers, and you would print out the summary of the day's total. So that would be a sentinel type control. If I want to do something 100 times, that's a counter. I'm going to use a counter. So these are two different types of loops that's there. If I want to calculate student grades, and I don't know how many students are in the class, I would have a last student indicator. That's there. So in counter controls, we have a control variable. Now, I mentioned earlier that normally most of us use I, J, and K for the counter variables because we started with Fortran, and Fortran required that integers be used for loops, and integers had to start with I, J, K, L, and M right there. So as a result, as old timers use I, he uses the word counter a lot. That's there. So I suspect that his father used I in the earlier version of the books, and the son has kind of updated the word counter because the son would not have grown up in the Fortran days. Right there. Sentinels is when we don't know how many. So those are the two types of loops: counter control and sentinel control. Right there. Counter control, we usually use the for loop, and let me just jump into it. Here we define counter as a integer. We initialize its value to 1. Now we can initialize it normally within the loop. The for loop usually has the initialization part in it. So this particular example is a while loop. Right here. While counter is less than 10. Counter starts off equal to 1, and we increment the counter every time we go through the loop. That's there. Now I could put the plus plus here in the print statement if I wanted to. We can combine those two right there. But this is a particular case where we're up there. This is a while loop. You know, there's that there. And normally we don't use that there, but again, that's a perfectly legit type of count loop right there. I'm not going to go through all the slides up there because we've gone through it there. When we exit the loop, the counter is equal to 11. As I recall, I typed this one in to show you. That's there. So here he does the while plus counter is less than 10. He does the plus here. You can do the plus anywhere, actually. Anytime I use the variable counter, come on in, that there. Anytime I use the variable counter, I can do the plus. It's considered kind of a bad programming technique to do that too often because it makes your code a little harder to read. But there's nothing wrong with it, and a lot of C programmers do that simply because they don't like to type. I'll be honest, since I can't use my right hand very well, and you've seen some of my typing skills, you know, here lately, that I tend to do more shortcuts now if I write code, simply because I'm avoiding the typing. So, and I suspect that probably 80%, if not 90+% of you in this room are not touch typists, right? Never took it. Did you take typing classes in school? So you do the 2-finger hunt and peck thing? That's there? Yeah, I do the 2-finger, except for I'm so used to use my two hands and typing this way. Unfortunately, my left hand moves faster than my right hand, and I make lots of mistakes, as you well see that there. You know, eventually, hopefully, the right hand comes back. But again, be careful that there. Again, he says right here, some programmers feel that this makes the code too cryptic and error prone. That's here. I really agree with using that plus in the while statement or even the printf. It's legit. You can do it. There's nothing wrong with it. If I put the plus after this here, it's going to increment this after it does the plus. If I put the plus before, it's going to increment it before it does the printf. So, you know, you can put the plus before or after it. If you do it before, it does the plus, then it executes the statement. If you put it after, it executes the statement, then increments this right here. Here, it's doing the plus, you know, before or after. It doesn't make any difference because it's in a line by itself right there. But it does make a difference here because it's going to do the plus before it does the compare right there. So, and notice here that he says that we have to initialize the counter to 0 to make this work because it's doing the plus before it does the compare. So we have to start off with 0. If we did the plus after, it would do the compare, then do the plus. So they behave differently, whether you have the plus before or after, right there. Right there, I'm going to skip all these. The for loop is the way you would normally do this. And right here, now, this is again something I don't like that he does. Right here, he initializes the value of counter in the for loop, which is perfectly fine, but he declares the variable counter as an integer within the for loop. I would prefer that he did this up here or even after the end. Yeah, that's there. And there is a difference when we get into chapter 5. If I put it here, it becomes what's called a global variable. We'll talk about that in the next chapter. If we do it here, it becomes a local variable. That's it. So, that's there. But he initializes counter inside the for statement, and that's, to me, that's considered, I would consider that bad. So the for begins, it initializes counter to 1, then it checks to see that it's less than or equal to 10, and then it increments the counter after the loop is executed. So as we go through here, it counts, starts at 1, checks is it less than or equal to 10, it runs the loop, then it increments the counter. Then it checks to see whether it's less than 10, it executes the loop, then increments the counter again. So the flow again is the first statement, the initialization statement, is only executed once. Then it does the compare, it executes the body of the loop, then it does the increment right there. So before it begins by initializing, it does the condition, satisfied, then so it'll execute the body of the loop, then it's increment, and it executes again. So this slide kind of goes through the steps right there. Because control is now 2, the final value, and it keeps repeating until the last time it increments, the value is going to be 11, so it's not less than or equal to 10, so it drops out of the loop right there. So the for statement does it all again right there. So this kind of goes through the control variable is counter. We put a semicolon between each of these are 3 separate statements. They're not all required. You don't have to have those statements in there if you don't want to. In other words, if counter is incremented somewhere in the loop, you can leave this last one off. If you leave the continuation condition out, then it just runs forever. Right there. So that there typically you have all 3 of these. The initial value of the control, the condition, and then the increment or decrement of the control value right there. And this just talks about the fact that if you use the less than instead of the less than or equal to, then it'll only execute 9 times. That's a common programming error. So again, this is the general format: initialization, condition, and increment. And then the beginning bracket and the ending bracket. And again, this shows a statement, but there can be 200 statements inside the body of this loop. Right there. And you can't put loops inside of loops. And you can put loops inside of loops. You can have loops, 10 deep if you want. Things get rather messy if you get more than 2 or 3, but you can have what's called nested loops. Right. Comma lists that they're usually I don't recommend using comma lists, and I'm not going to talk about using the comma list. That's their primary. And expressions in the for loop are optional right there. If the condition is omitted, C assumes that the condition is true, creating an infinite loop. I mentioned that already. You can eliminate the initialization if you initialize it somewhere else in the program, and you can eliminate there. So you could have loops right there. So here. Now, the increment X is a standalone statement that C does do this shortcut plus equal 1. That means the counter is equal to counter plus 1 right there. This is pre-increment, post-increment right there. You do need the 2 semicolons right there. Even if you eliminate, you have to have the semicolons right there. And again, here's a case where we initialize that J is equal to X. We're going to execute as long as J is less than or equal to 4 times X times Y. And we're going to say that J is equal to Y divided by X. So again, this is a more complex for loop. Normally, I don't recommend making them this complex, because then you have to go through and calculate, is this there? But there are times that you'll do that. The increment may be negative. Right here. This is trying to find one of the words, increment. I don't care about the full chart. Here's a case right here, the second one is I is equal to 100. As long as I is greater than or equal to 1, we continue the body of the loop, and we decrement 1 from I each time. Here, we're going to add 7 to I each time. I is plus equal to 7. Here, we're going to subtract 2 from I each time. And notice that he's gone back, he's using the dad's slide, so he's gone back to I as I normally do. Right there. Here, he's incrementing j by 3 each time. Here, he's subtracting 11 from j each time. So evidently for this slide, he didn't want to do a lot of typing with the word counter. So he used I and j. Right. And limit the size of the control statements to a single line if possible. In other words, don't make them too complex. Up there. This is just, I think I did this in class and not. Go through and enter. This is just goes from 2 to 100 plus 2 each time and just adds 2 to the sum each time right there. And then prints out the final answer at the end. Right there. So I think this is the one I did in class right there. This is pretty much where I ended the last class. The compound interest. That says if I dump 1,000 ringgits into the bank, making 5%, what's it equal to in 5, 10 years right there. So this particular one, we start off with 1,000 in the bank, where our rate is 5% interest right there. And I challenge any of you to find a bank that's paying 5% interest today. I think typical is 2%. But they're in the U.S., it's like 1.5%, 1.25%. Interest rates are through the toilet, but that's what they are. So we're going to print out the headers. And notice that we've got a percent for S. That means we're going to it's a string of 4 characters. Then we're going to, actually this starts at column 4, starts at column 1 right there, and we're going to print year and amount on deposit. And we're going to print this out every 10 years. We start with year 1 and we do it up to 10 years. You could do it every 5 years, up to 50 years, or however long you want to run this particular formula through here. This uses a function called power. This is principal times 1 raised to the rate, or power rate raised to the year, right there. So this particular is raised to 1.05 raised to the year right there, and we take our 1,000 times that, and that's what is the result of this right there. And don't be giving me that stuff right there. And this just prints out a table right there from 1 to 10 years right there. So it's a nice, neat little exercise. If I that there, and I think I did this in class just before the break, didn't I? Right there. And this is what it says. So my 1,000 is equal to 1,600 at the end of 10 years. And as I recall, I mentioned that about 8% interest doubles about every 9 to 10 years. So if you took 1,000 ringgits, put it in the bank, and left it there for 30 years at 8% interest, it would be somewhere right around 2,000, 4,000, 8,000 ringgits at the end of 30 years. So that's the beauty of compound interest. That there. So the secret is save young. That there. So the for statement there calculates, and this just goes through this in more detail. Notice that if I'm going to use the power function, I have to include math.h. And math.h would be used if I include sine, cosine, tangent, any of the other math functions. So that's another header file that contains the information. That's a common mistake students make when they start writing programs that use the power function. Right? And this talks about that. The function prototype is included. So, and we'll go through that. Caution for float and double is that there we define the variables amount, principal, and of type double. That's there because of the fractional parts of the dollars. You can't declare them as integers because dollars have fractional parts. That there, we're raising it to 1.01 or 1.05, so it may be fractional. Double is a floating type, but typical. It does have a higher resolution than float. Float is typically a 16 or a 32-bit number, where double is a 64-bit number. It tends to be a little bit more accurate. That there. So if you're dealing with financial issues, double is almost always the case, right there, because you need the accuracy. Right there. Even though they calculate pay based on, down to the cent, not to the fraction of a cent. When banks keep track of information, those fractional parts add up. That there. There was actually a situation where somebody one time took all the fractional parts of interest calculations in checking accounts or savings accounts and put all the parts that were not shown and put it in his own account, and it came out to millions of dollars. He actually went to jail for it, so he didn't get away with it. So that there are two float values. That there, again, this particular format right here, %.2f is telling you that you want your answer to be shown with an accuracy of 2 decimal points, right there. So that's there. So, and this is an example of, here we're going to add up 14.323 to 18.27. But again, that's what it will add up to. But if those numbers are 2.34 and 18.63, so that comes up to 0.7. That doesn't show up. But when we print it off, it looks like there's an error there. In reality, it's an error because of the resolution of the printing. If we did an f.3 on the printout, we would have seen that fractional cent show up. So again, 21.2 means that the width of the field is 21 characters, or 20 wide, and we show 2 decimal point that there. So these formatting strings can get more complex. As you look back here we do %4s. That means we're making that 4 characters wide. That field is 4 characters. Here we're making it 21, and it's going to be right justified, right there. And again, here we're doing our %4 to make that 4 characters wide. It's unsigned integer, but we're going to right there. And then our next field is 21 characters wide is the width of the field, and it's going to have a 0.2 floating point. There wouldn't be a U.2 because an unsigned integer doesn't have any decimal points. So you wouldn't have any numbers to the right of the decimal point. The only one you would have that is on a float or a double. That's there. And notice that it uses F for float, even though we declared it as type double. D in the formatting string means decimal, which we could use decimal there if we wanted to. Right there. And we could put a $sign in that that sign that there. So, okay, as I said, I'm flying through these. I'm halfway through the slides already. Right there. So, okay. To right justify, you put a minus sign in front. So, or left justify. Normally, they're right justify. Means everything's moved to the right. Put the empty spaces before. But you could do a left justify by putting a minus between after the percent. And that puts it to the left of inside that field. That's there. So here, percent negative 6D means that this is a decimal right there. So which is a integer right there. And it's got a field width of 6, and it's going to be on the left side of the field, not to the right side. Here, minus 8, we gave it a field size of 8. It's a string. Now also note that if you give a field size less than the number of characters in the string, it'll truncate the string. Right there. And series of decisions. All right, this is kind of the last topic for this chapter, right there. And this is the switch statement. And the switch statement is a replacement. We've already talked about the if-else statement. That was chapter 3. Some of you forgot the if-else statement. I know you've slept since then, you've taken a week of vacation. But the switch statement is a multiple selection. It allows us to make a decision based on a variable, and we can have 2, 3, 5, 50 different choices for that variable right there. And it eliminates the need of having multiple if-else statements right there, or multiple if-else statements right there. So here's an example of it right here. We start off with the number of A, B, C's, D's, and F's in a class is 0. And we're going to do something a little different here. Enter the letter grades. Enter the end of file character to end the endpoint. The end of file character in Windows is a Control Z. So, that there. So, int grade. So, we're going to enter a grade. While grade is equal to get char reads the keyboard, and you print A, B, C, D, F in there, is not equal to end of file. That's a whole new, this is a whole new structure right here. While grade is equal to get char. So we're going to read the keyboard, and the person's supposed to type in A, B, C, D, or F right there. And we're going to compare that to this capital EOF. EOF is a reserved word in C that means end of file. Every file stored on your computer has, as the very last character in that file, a control character, Control Z. And that tells the computer when you read the file, that's reached the end of file. Now, in this particular case, we're not reading the file, we're reading the keyboard, so we simulate the end of the file by hitting the Control Z. Now, we could rewrite this where it goes grade is equal to file get char, where it reads a file and gets all the names of a file. We haven't done files yet. So we're going to use for our file, our standard input, which is the keyboard right there. Now we're going to do the switch. Switch, and we're going to look at grade right there. Grade is what we've inputted. Now grade is either A, B, C, D, or something else. Now it's a single character. That there. And the reason we know it's a single character because we use the get char command. We didn't use scanf and %s, which reads a string. That there. We used a function called get char that only returns back a single character. And we still have to hit the carriage return. That's right. So switch grade. If it's an uppercase or a lowercase grade, we increment the number of A's. We put a break so we don't bother checking the rest of the grades right there. If it's a B, we increment B. If it's C, that's it. And F, now we also have ignore new lines, ignore tabs, ignore spaces, break right there. We have a default, which is %s. We're going to print out incorrect grade entered. Please put in a new grade. So if I, that's there, optional break. And again, that'll ask that there. And this just keeps repeating until our get char is equal to the end of character right there. This is a while loop. It's going to repeat until the get char is equal to EOF. And in this particular case, that there, and then it just does the print S, and it just prints out the number of A's, B's, C's, and D's, and F's for them. So it's a relatively simple program that we just keep putting in A, B, C, D, F, A, B, C, D, F. It doesn't matter whether it's upper or lowercase because we handle the upper and lowercase right here. There are other ways to handle upper and lowercase, but this is the easiest way right now. There's a function called toUpper or toLower that converts it right there. So that's a simple little program that uses the switch right there. And again, we entered an E. It gave me that there. Here, Control Z. You may not see the Control Z right there. And then it shows the number A, B's, C's, D's, and F's for the class. So it's a relatively short program for doing that there. So again, this kind of goes through the same thing that I talked about that there. I'm not going to go through and read these slides. I've already explained this as it went along right here. Okay, we can treat a character, print the character as a value of D. This actually tells us that if we look at the ASCII, there's a character here. We're going to tell it here, if we print it as a %C, it's going to print the lowercase a. If we print it as D, it's going to print the ASCII value, and you can look up the ASCII table. That's a table that has all the characters in a value form right there. So we can treat a character as a number, and we can treat a number as a character. Right there, characters can be read using the scanf. And I mentioned that we could use the get char a scanf and put a %C in there. So, okay, a couple of other things useful. This is kind of an interesting statement. I don't like it. But he's saying A is equal to B is equal to C, and they're all equal to 0. So this initializes A, B, and C all to 0 at the same time, right there. So that's there. It is just one of those interesting things that you can do that. I'm not sure. I don't like it. I don't do it in my programs. Do multiple assignments, but you can do it. That there, Control Z, that there. So I have no, that there. We've chosen to represent characters as ints because EOK as a normally -1, but that there I'm going to skip all that. Control D is Unix and Mac and a character. It's different than it is for Windows. And I'm nearing the end of where I want to finish. The switch, the details, the controlling expression, and then we have the case labels. Now, one of the things here is that you can't have in the switch case less than 10 or something like that. It's got to be a set value. You can't do less than or equal than 2 inside there. It's always equal to right there. So there are some limits on the switch statement right there. The default is optional, but you should almost always include it right there. The default is the one that's executed if nothing else is found right there. And if you don't use the break, the default will almost always be executed anyway. So you want to do the break. So if the break is not used anywhere, then each time it occurs in the statement, for all the remaining will the follow through. So if you don't use the break, it doesn't skip the rest of the comparisons. So it'll end up doing the default regardless. So the break is really needed. If you notice that in this code here, you put the break in each and every case. Otherwise, if you left the break off, then it's going to execute right there. And also notice that he ignores, he has 3 case statements here: case, new line, case tab, and case space. He's ignoring all 3 of those. You can list multiple case statements and only 1 set of code. Here we have 2 case statements and 1 set of code right here. Then the break right there. So again, the flow chart, I don't care about the flow charts right here. Again, this does 3 right there. So if you don't include the no line in there, you'll end up with an error because they'll read that as 2 characters. We can list the 2 on the same line right there. That's perfectly fine. Using the switch, remember, each can only test a constant integral expression right there. So characters must be enclosed right there. You should avoid float and any kind of double as types because exact values almost always use either character or that's there. I'm going to kind of skip through this right here. Long int, char, up there. The do while is up there. Is another one. It's just like the while, only you put the while at the end of the loop. The only difference is that the do while is executed every time at least 1 time, because it does the comparison at the end of the loop, where the while does it at the beginning of the loop. Right there. They behave very, very much the same way. Right there. And not all languages have a do while, but most do now. That there's not necessarily use braces. That there because there's only one. If there's only one statement, you still need the braces. And then you do while. You start with a do and then an opening brace. Right there, and then the while at the end. And yeah, here we have an example of that. Do while counter is less than or equal to 10. We do a plus counter beforehand. So we increment counter each time through the loop before we do the comparison. and we get to 10. If we did the counter plus plus at the end, we would actually go from 2 to 11. Right there. Because if we put the plus plus here, it'll do the comparison, then do the increment. Right there. So, again, we have the break and continue again. I don't use the continue too much, but that's there. Or I use the break a lot, but the continue I don't use too much. Right there. So break only if x equals 5. So what this is essentially saying is, that if I run this, we're not going to print x if it's equal to 5. We're going to skip that particular printf, the rest of the body of the loop. So this will print 1, 2, 3, 4, 6, 7, 8, 9. It skips the number 5 because I have a break only if x equals to 5 right there. So that's it. So again, we use continue to continue. That's there. And the and or, I guess I need to kind of spend a few minutes on that there. So I was going to talk about how that's there. Logical and the or, you'll see those in some examples here, but that there. Those are ways of making our if statements and our conditions more complex. If gender is equal to 1 and age is greater than or equal to 5, in this particular example, one is a female, so we've now incremented the number of senior females to 1, or golden female citizens. That's there. So that's there. So both conditions have to be true in order to increment. That's there. I would have to assume else if age is greater than equal to 65, number of C plus plus senior males right there. So it is one of those cases right there. But we're looking for a condition that the gender is equal to 1 and the age is greater than or equal to 65. Both conditions have to be true right there in order for this to happen. Right there. So if one or the other is false, it doesn't happen. Right there. So but they're both there. And when you take digital electronics, you probably have seen these truth tables before. The or is the two signs. That's the capital, if I can find that on the keyboard. It's on the right-hand side above the enters keyboard. That there, the little pip plus plus or right there. And so if grade, the semester grade is greater than 90, or the final exam grade is greater than or equal to 90, we're going to give the student an A. I've done that in the past where I've, here UniKL, you have to put in all the grades and then they automatically calculate the grade for you, and the instructor can't override the grade. Back at Purdue University, where I used to teach, university didn't have any rules on grade. The professor could do whatever they wanted. I could look at you and say, all right, you deserve an A because of I like the shape of your glasses. That would be a little, biased, and people would complain if I did that. But as a professor, I could do whatever I wanted. And I used to, for example, say that my final exam was optional in a class. If you had a 90% average going into the final exam, you didn't have to take it. If you took the final exam, I would only count it if it helped your grade. If it hurt your grade, I would ignore it. And if you've got an A on the final exam, then I would give you an A in the course, regardless of what you did up to that point. I used to have some funky rules like that I would do from time to time. That's there. And like I said, here we're not allowed to do that. But this rule here looks like something from, where the professor says that if you get an A on the final exam, I give you an A in the course. I've had classes that allowed that. I don't think I've done that too much, but I've always thrown the final exam away if it hurts you. I've done that a lot on optional final exams. I made the final exam optional, and the general rule is if you're sitting with a 75, which is a C under the American standard, chances are you're not going to raise your grade. But if you're sitting there with a 79, then an 82 or 83 on the final exam could raise you up to a B. So I would allow students that so students would go through and they would calculate their grade, and if they were in the middle of a grade field, then they wouldn't take the final exam. If they were toward the bottom of the grade field, of course they wouldn't take the final exam, because if you're sitting with an 81, in order to get an A, you'd have to get 103, for example, on the final. It wouldn't make any sense. But if you're sitting with an 88 or 89, then by all means you're going to take the final exam. It was that kind of logic that people would use. But that's what was going on in this particular case, is that the semester grade or final grade exam is greater than 90, then the student would get an A. That's an or case. So under this algorithm, a student could do no homework, get a 0 on all their final exams, ace the final exam, and get an A. I never did that. That's it. So those are the two logical answers. And we can combine those into all kinds of that there. If not grade, if the grade is not equal to sentinel value, and that exclamation mark is in front of that there. And you could also put exclamation mark equal to as well. That's also allowed. As shown right here. And here's all the various rules that you have. Now, there is another data type called Boolean that evaluates true or false. That's there. And if you include type Boolean, you have to include standard Boolean as a header file. And you quite often will use Boolean if such is true or false right there. So C++ doesn't implement that. Keep in mind that equal, and equal are not the same. I think I mentioned that earlier with the if statement. Right? And this goes into that more detailed. If you say if pay code is equal to 4, you get a bonus. But if you accidentally say if pay code is equal to 4, what that does is it makes pay code equal to 4. If it wasn't, it gives the employee a bonus every time. Right? So they're not the same. And I think this just goes on to more and more. This goes into more detail you don't need. And that there. If x equal to 1 assigns x equal to 1, if we write x equal to 1, it just compares x to 1, but since it's not an if else, it just ignores that statement. It doesn't do anything. I'm not going to go into this in great detail. Structured programming just simply says you should have a single entry point and a single exit point for every loop or every program that they're single input, single exit point. I'll let you read that this is getting into structured programming techniques right there. And if this was a longer and more in-depth course, I would probably spend more time on to that there. And I think I'm going to wrap up this chapter at this point right there. The scanf actually returns a value right there, and I'll talk about that in more detail as we get into functions right there. Scanf actually returns the number of variables read. If it returns a 0, then it couldn't read anything. Here it's going to read 2 numbers, so it'll return 2. We can also, in our scanf, we can check, make sure it's entered in a range. We'll do that a little bit more detail. And that wraps up this chapter. I said before the break I was going to finish this chapter in one session. I did it this time, but I skipped a lot of slides toward the beginning. I talked pretty quick, so I think Wednesday I'll probably have you do on this talk just for a little bit, and then have you do some programming. That's there. This was a pretty boring lecture. Put everyone to sleep, right? Well, I only talked 15 minutes to cover 150 slides. That means I averaged 3 slides a minute.